This video is about periodicity, which refers to the repeating trends in element properties on the periodic table. These are the physical properties of interest that we will cover. These properties explain the periodicity of chemical properties that we will look at later on. Let's start by reviewing what we already know. A group refers to the vertical column on the periodic table. Elements in the same group have the same number of valence electrons. For example, these elements here in group 1 all have one valence electron. A period refers to a row on the periodic table. Elements in the same period have the same number of electron shells. For example, these elements in period 3 all have 3 electron shells. Let's now look at the 3 main factors that affect the physical properties of an element. The first one is atomic number, also known as nuclear charge. Each proton in the nucleus adds a charge of +1. The more protons there are, the greater the positive attraction is. This attraction pulls electrons in towards the nucleus. You can see here that the positive or nuclear charge of the nucleus containing protons pulls the negatively charged electrons towards it. This positive-negative attraction is called electrostatic attraction. The second factor is the electron shells, or the distance between electrons and the nucleus. Each shell level is further from the nucleus than the one below it. You can see that here in this diagram. The third factor is shielding. Because each electron has a negative charge, electrons in lower levels can partially shield an outer electron from the positive charge of the nucleus. In this atom, we have an outer shell electron, and the electrostatic attraction pulling it towards the nucleus is partially blocked or shielded by this inner electron. So we know that nuclear charge refers to the number of protons an element has. We often refer to an element's effective nuclear charge, which is less than the full charge due to shielding. It is determined by the following equation. You can see in this image that what's involved in the effective nuclear charge are the inner electrons that shield the outer electrons from the nucleus. The outer electrons we're interested in are the valence electrons, and the inner electrons are everything else. So how do we determine effective nuclear charge? Let's look at sodium. It has a nuclear charge of 11, which means it has 11 protons. We can see from the electron configuration that it has one valence electron and 10 of the electrons are inner electrons. So to find the effective nuclear charge, we're just going to do 11 minus 10, which will give us an effective nuclear charge of +1. This will work the same way for these other 2 examples working across the period. However, as we gain a proton, the effective nuclear charge will increase by 1, since the number of inner electrons is not changing. So going back to our formula, what do these things actually mean? Well, ZF refers to the effective nuclear charge. Z refers to the nuclear charge or the atomic number of the element, and S refers to the number of electrons in the inner shells. Let's have a look at the trends on the periodic table. Consider our equation once again. If S is smaller, ZF will be larger. So essentially what this means is as we have less electron shells, the effective nuclear charge will be greater. So it increases as we work up the groups. If Z is larger and S stays the same, so we gain protons, but we don't gain any more inner electrons, then ZF will be larger once again. And that's because we're going to have a greater nuclear charge without any more additional shielding. Let's move now to atomic radius. This periodic table shows relative atomic radius of different elements. Let's look at the first trend. The atomic radius increases down the group as the number of electron shells increase. So more electron shells results in a larger atom. We could also say here that more electron shells results in more shielding, which reduces the which lowers the effective nuclear charge. This results in a larger radius, both of these factors. As we work from left to right, the atomic radius decreases. This is because the nuclear charge, or the number of protons, increases. So more protons results in a smaller atom. This is because that nuclear charge is pulling the electrons in towards the nucleus. So it's pulling the shells in closer. The atom is going to be tighter and therefore smaller. Let's move now on to ionization energy. So what is it? Ionization energy is the energy required to remove one electron from each atom in a mole of atoms, and it is measured in kilojoules per mole. This process is always endothermic. What does this mean? It really means that in order to remove an electron from an atom, you need to put in sufficient energy to break the attraction between the nucleus and the electron. We refer to ionization energy as first ionization, second ionization, etc. First ionization is where we have our atom and we take one electron away from that neutral atom. So we now have an ion with a charge. The second ionization is where we take that ion with a charge and we remove another electron. Now we can keep doing this essentially until we run out of electrons. Now, this property is really important because it is related to reactivity. For example, potassium has a low ionization energy of 419 kilojoules per mole. This means that it is highly reactive, and potassium usually is found in a compound. So basically, it doesn't require a lot of energy to remove an electron from a potassium atom. Gold, however, has a high ionization energy of 890 kilojoules per mole, so it takes a lot more energy to remove an electron from a gold atom. This means it is less reactive and it is less likely to be found as a compound with surrounding elements. Let's look at the trends on the periodic table. First trend, as we gain protons, the ionization energy increases. So it increases from left to right with nuclear charge. That's because that nuclear charge is once again holding the electrons in towards the nucleus, so it's harder to remove the electrons. Now, as electrons are further away from the nucleus, the ionization energy decreases. So it decreases from top to bottom. Alternatively, it increases from bottom to top. That's because when the electrons are further away from the nucleus, the attraction keeping them attached to that atom is less, so it's easier to remove them. Similarly, more shielding from electron shells reduces the ionization energy. So ionization energy decreases from top to bottom. Electronegativity. So the definition is the tendency of an atom in a bond to attract bonding electrons to itself. Now, this characteristic only really manifests when the atom has bonded to other atoms. Let's look at an example. Here we have a Lewis structure of an oxygen atom, and we now are going to add the Lewis structure of a couple of hydrogen atoms. This is what we call a covalent bond because these atoms are sharing electrons so that they have a full outer shell. You may recognize this as a water molecule. You can see that the electrons are spending more time closer to oxygen than hydrogen. This gives oxygen a slightly negative charge and hydrogen a slightly positive charge. We call this a dipole, and you can see that we represent this with delta negative and delta positive. So this means oxygen has high electronegativity and hydrogen has low electronegativity. Now, this is an interesting property because if we were to have another water molecule nearby with the same electronegativities, then the negatively charged hydrogen on this molecule will be attracted to the positively charged hydrogen on this molecule will be attracted to the negatively charged oxygen on this molecule. And this is, once again, electrostatic attraction. So this means water molecules behave a little bit like magnets. Let's look at electronegativity on the periodic table. Our first trend, as we gain protons, we have a higher electronegativity. So it increases with nuclear charge. And that's because the positively charged nucleus with more protons is going to have a stronger pull on the electrons that have bonded to that atom. As electrons are further away from the nucleus, electronegativity decreases. So it decreases with the number of electron shells. And that's because it's harder for the nucleus to attract those bonding electrons when they're so far away. And similarly, as shielding increases, electronegativity decreases. We have more electron shells. That strength of the nuclear charge is reduced. So electronegativity decreases as we work down the periodic table and increases as we work across from left to right. Finally, this is a bit of a summary of all the different properties we spoke about in this video all together on the periodic table.